Great. Hey everyone, I'm really glad to be here. My name is Rustamkulov, and I'm excited to tell you all about my most recent work on characterizing the ages of main sequence stars. So in 1630, Johannes Kepler first forecasted the transit times of Mercury and Venus. The first transit of Mercury was observed a year later, right after he passed away, unfortunately. The first transit of Venus was observed in 1639 and gave a rough constraint of the value of the AU. Transits of Venus in the 18th century refined the value of the AU and gave the first percent level constraint of the sun's mass. Transits in our solar system are rare and have long contributed to our exploration of stars and planets. Likewise, the transits of exoplanets are now enabling an entirely new perspective on planetary science. By combining Kepler's third law with the density of a sphere, we can link a planet's transit duration with the bulk density of its parent star. With a stellar radius constraint, the stellar density provides the information needed to constrain the planet's semi-major axis and the star's mass, which is needed for characterization. Eccentric orbits complicate this picture, but I'm telling you about planets that are close in and probably tidally circularized. So stars of similar mass and composition are expected to have similar interior structures. Sun-like stars are mostly ideal gases with negligible radiation pressure and degeneracy pressure. Homology relations give us helpful approximations for investigating stellar structure. As a star accumulates helium in the core gets denser as its mean molecular weight grows by a factor of roughly 2.5. The envelope responds by expanding. This expansion is inversely proportional to the change in the mean molecular weight of the core. So here are the density evolution tracks for sun-like stars ranging from 0.6 to 1.4 solar masses using state-of-the-art models, MESA. The colors of the lines are what you would actually see with your eyes. This figure shows why supernova scientists are bored by main sequence stars. They hardly change for billions of years. If you look closely, you'll see that the densities of all the stars fall by roughly the same fractional amount, a factor of about 2.5. So when the mass and metallicity of a star are known, a bulk density constraint is informative of the evolutionary state of the core. And if you overplot the prediction from homology, you'll find that the curves agree surprisingly well. Stars inflate predictably. Aging also affects the transiting planet's light curve. Here I'm showing an animation of a hypothetical hot Jupiter transiting the sun. As the sun inflates, the planet's transit depth increases while its transit duration grows. Here's another perspective of the same thing. As our star grows with age, A over R star drops off, the transit duration gets longer. Before JWST, in the ground-based era, typical A over R star uncertainties were on the order of 10% or worse. That's mostly because limb darkening at optical wavelengths is quite strong. It's degenerate with A over R star and with impact parameter, even at high signal-to-noise. Here's an optical transit light curve of WASP-39b taken with JWST's near-spec prism mode. This is everything blueward of 0.7 microns. You can see the limb darkening is quite strong, and the ingress-egress contact points are kind of blurred out, and the transit bottom is U-shaped. Now here's the full prism transit white light curve, which covers 0.5 to 5 microns. WASP-39b's transit bottom is much flatter, and the contact points are much better defined. Thanks to the weaker limb darkening in the IR, JWST's ultra-precise light curves constrain A over R star an order of magnitude better than ever before. This means we get precise stellar bulk densities of better than 0.5%, which is mind-blowing. Let's have a closer look at WASP-39. It's a hot Saturn system, and it was discovered in 2011. The isochronal age estimate in the discovery paper is unremarkable probably because the distance is uncertain by a factor of 1/3. Also, the mass is only good to about 10%, and the radius is uncertain by 1/4, so it's no wonder that you can't get a good age from these data. The pre-Gaia times were rough. Now, this is the first time that we have precise distances, temperatures, luminosities, and densities of nearby suns. It's pretty challenging to infer the ages of main sequence stars, especially when they're middle-aged. Gyrochronology and the lithium indicator are mostly sensitive to younger ages, and gyrochronology is potentially biased by tidal interactions with the planet. Astroseismology requires extremely high precision, high cadence photometry, or RVs, so it's expensive and you don't get it very often. The observable properties of main sequence stars change extremely slowly, so without a mass constraint, the age becomes lost in degeneracy. But why do we even care about the ages of planetary systems? Hot Jupiters have been confusing us for a while. How did they form? When or did they migrate in? Why are they so puffy? These are all quite unknown. So having their ages would give some helpful context here. Precise ages would help unlock the thermal evolution of planet interiors. Today we have access to space and ground-based multi-band survey photometry that lets us measure the fluxes and colors of many nearby suns. And thanks to the wide wavelength coverage, we get really good effective temperature estimates. Here's the panchromatic SED of WASP-39 as assembled from SkyMapper, Gaia, 2MASS, and WISE photometry. It's pretty well fit by a Planck blackbody curve, which gets you the temperature to within a few percent, and then if you use stellar model atmospheres, the effective temperature is often better than 1%. Gaia measures an ultra-precise half% uncertain distance of 212 plus or minus 1 parsec for WASP-39. We make sure to adjust this value by the 0-point offset and uncertainty. So now that we have WASP-39's SED and parallax as inputs, we can explore the range of allowable stellar properties that can explain the data. We use the isochrones Python package to jointly fit survey magnitudes and the parallax. Here's the resulting distance radius posterior of WASP-39. And these are the posteriors on our input magnitudes. We make sure to adjust the magnitude uncertainties by the 0-point uncertainties inherent to each survey and each bandpass, which are typically on the order of a few percent. This is the same thing for the K-star HD 189733. We find reduced chi-squared values of 1 and below, which means that we've correctly adjusted our uncertainties on the input magnitudes. So we deeply sample the model grid to generate a posterior in age versus stellar density and find a 2 gigayear age uncertainty and a 10% density uncertainty. Then, when we fold in the transit density, the posterior collapses. We get an age of 7.3 plus or minus 0.6 gigayears. That's a sub 10% fractional age uncertainty. We also find remarkably precise stellar mass of 0.9 plus or minus 0.01 solar masses, which is 10 times more precise than the Discovery paper, sorry. We didn't come up with this technique. This method was first performed by Alessandro Sozzetti et al. 2007 and was applied by nearly a dozen other authors, a dozen other papers. We did the same exact thing for HD 189733 and found an age of 1.6 plus or minus 0.6 gigayears, which is older than the age implied by gyrochronology. To test the reliability of our procedure, we applied it to a very well-studied nearby wide binary system in the Kepler field. BD plus 45 is a pair of well-separated sun-like stars with exquisite astroseismic constraints of their interiors. We used the precise seismic density measurement as a constraint on our isochrone posterior. We find excellent agreement with the ages reported from seven different seismology models. And most importantly, we find ages that are concordant with each other, which makes sense since the stars formed at the same time. We also get radii and masses for the stars that agree quite well with the astroseismologists, despite the stars having pretty different masses. Our error bars are tighter, probably because we use Gaia DR3 and they use DR1. This is an older study that we're comparing to. There are a few important considerations about the systematic uncertainties here. While we can account for 0-point uncertainties in the filter magnitudes and the Gaia parallax, it's harder to account for differences between stellar models. Scrambling the mass posterior and reapplying the density cut is one way of approximating the systematic model uncertainties. This gives a typical systematic mass uncertainty of more like 2%, and this should be evaluated on a case-by-case basis. While we quote super precise ages, in reality we expect an absolute age uncertainty floor of about 15% due to differences between models and the uncertainty in the star's initial helium fraction. So here's a plot showing effective temperature versus the rotation rate of some stars that I looked at in this work. We've known for a while that hot Jupiter hosts spin faster than similar field stars. This may be due to tidal interactions between the planet and the star. In the case of 189, the star's rotational period is about 5 days faster than expected at its measured age, possibly indicating tidal exchange with the hot Jupiter. The orbit is circular, so we know that tides have been happening or have happened in the past. This amount of excess angular momentum corresponds to 0.03 AU of inward migration by the hot Jupiter. By integrating differential equations of tidal evolution, we find that a constant value of Q star cannot reconcile this amount of migration with the planet's present-day orbit. This might be evidence for variable tidal efficiency with age. We can also confirm that HD 189's, the planet's slight excess in interior heat cannot be attributed to primordial heat, since the planet is several thermal timescales old. So I've applied this technique to measure transit ages for about 10 planets so far. The data I'm showing here span planets orbiting a diversity of FGK stars and even an A star, WASP-178. I'm showing the 15% fractional systematic age uncertainties as gray error bars. There isn't a clear trend between semi-major axis and age. Could this be a sign of high eccentricity migration? I actually am not sure. So here I'm showing the planet density, which is a rough proxy of its interior heat as a function of fractional main sequence age. There is a tentative downward trend showing that perhaps planets inflate as they age, which is supported by the analysis of Thorngren et al. 2019. More ages for a more controlled sample of planets would let us compare different evolutionary mechanisms. And here's my last point. If we simulate the expected JWST transit density uncertainties for everything on the Exoplanet Archive database, we find that over 600 systems can give sub% stellar densities. This means that we can get the ages of hundreds of systems, letting us explore the mechanisms of planetary and stellar evolution. Thanks.
All right, questions for Zavar? All right, Eric has been waiting patiently. We'll go with him.
It's only for 3 seconds. This is great seeing the error bars decrease on the ages. I love it. I'm worried about accuracy rather than precision. I guess one thing I'm wondering about is, what do you think the prospects are? You had that list of issues you were worried about with the systematics. The big one with K-stars, I tend just not to trust isochronal ages of K-stars. Like we just saw one 10 minutes ago. It was 11 giga-year-old FE over H of 0.1 star. The galaxy was not producing FE over H of 0.1 stars 11 giga-years ago. Do you see prospects for improving the big one there probably is the helium abundance. Do you think there's other techniques that we could use to improve our estimates, maybe of the helium or some of the other parameters to improve the models?
Yeah, well, I would have said interferometry and seismology combined, but there still seems to be some tension for these K-stars. Maybe if we get a bunch of really good densities for a bunch of K-stars, perhaps with well understood, like in binary systems where the primary is a more massive, better characterized star, then maybe we can start to build up our statistics and empirically try to resolve the issue, but I'm not so sure.
Okay, I think we have time for one more. If we can get our next speaker to come down and we'll start getting them set up.
We have a question online. Do you see a correlation with incident flux?
Good question. I didn't check that yet. Thank you.
All right, we can go ahead and thank so far.